Okay, I know that you are eager to jump into the SolidWorks and create the simulation and see the results, right? But it is always a great way to go through the theoretical backgrounds that what we are trying to do in this video. So it is random vibrations, right? So as the rocket is launching, there are random vibrations that are generated, and the PocketQube satellite or any structure that is inside the rocket has to be designed in a way that it survives that launch vibrations actually. So okay, what does a random vibration consist? It consists of a spectrum of frequencies with the amplitude of these frequencies varying randomly. Yeah, that's the thing with the random vibration. We don't know the amplitude of those frequencies, right? So on the launch vehicles, random vibration sources include engine vibrations and acoustics. Obviously, you might have seen a rocket launch. There are big engines firing gases out, and it really creates those vibrations, and it is extremely important, right? Yeah. So statistical methods are used to describe random vibrations loads because there is no inherent mathematical way to describe a random vibration time history. Yeah, that is the case. So we are not looking at a particular vibration amplitude. We are actually looking at a spectral of that. Okay, spectral of that. So GRMS is the root mean square of the accelerations in a random vibration history. All right. So we gotta remember this. GRMS. It is not acceleration due to gravity, but it is just accelerations. Let's say during the rocket launch, there is a history of random vibrations, right? So for that, it is the root mean square of those accelerations during that launch period of time. Okay, and this is the common way of describing magnitude of random vibration accelerations. 1 sigma value of acceleration. If the mean vibration is 0, this means that statistically about 68% of the acceleration time history will be below GRMS. The peak response is generally assumed to be 3 sigma. Okay, this is just the properties of normal distribution, I guess. So let's move ahead. What we need here is the magnitude of random vibration varies for different frequency bandwidths. For this reason, it is beneficial to divide into smaller frequency bandwidth. This lets analysts to use. Okay, so what we do is we check this value root mean square acceleration. uh, Root mean square acceleration, we square that to get sort of acceleration and power frequency. So we want to look at this acceleration in random directions for a spectrum of frequencies, right? And we use that to describe random vibration amplitude uh, for each bandwidth. So it's calculated squared and divided by the bandwidth. Okay, so for each bandwidth the GRM is calculated squared. Okay, so it is talking about how this g square upon g square per hertz value is being calculated, right? So for example, if the RMS between 10 hertz and 20 hertz is 1.2 G's, okay, 1.2 times the acceleration due to gravity. So in that case, we know the frequency and the acceleration at those frequencies as well. Then we need to calculate g square per hertz value for that 10 hertz bandwidth, and it is calculated using, okay, you know this, right? So the difference between the frequency that we are looking at and just, okay, it is basic mathematics, you can look at that. So in SolidWorks we are going to actually define a curve for the random vibration. We'll define a curve, and I will be putting values in that starting from 20 going all the way to 3000. Okay, going all the way to 3000. And okay, so this looks to be a different distribution than what I am going to put, but this is the AST plot, right? So it gives g square per hertz with respect to different frequency, and this is what is sufficient in defining the vibrations for the structure. And we will need loading as well in the simulation. So with the information of loading and this AST plot, with AST plot, we can actually get the simulations results. So yeah, you can pause the video and look at these descriptions in detail if you want to know more, but you need to have this general idea of what we are actually going to do. Okay, so I'll be diving in the SolidWorks. Okay guys, the purpose of this video is that I want to show you a process of simulating the effects of random vibration in a PocketQube satellite. This is a simplified model of 1P PocketQube. 1P PocketQube means its dimension, it is basically a 50 mm cube, alright, 50 mm cube. It is sitting upon a sliding plate. The sliding plate will be attached, or it will be on the deployer, right? If the sliding plate goes in on the deployer, and it is kind of supported in its edges by the deployer. What we want to do now is we want to simulate the vibrations that are induced in this part during the rocket launch. Okay, so for that, okay, one thing is these are all different step files and that are put in an assembly, and these white parts are the aluminum blocks. They are made of aluminum. These yellow ones are brass rods. They are basically screw rods. So in actual satellite there would be screw rods, and there would be nuts over here and here and over here as well. And screw rods and bolts, not bolts, sorry, nuts, and they are going to be attached, and this is going to be the structure. So these are going to be the onboard computer system, EPS, and battery charging. All right, okay, EPS and stuff like that. So the circuit boards are going to be inside, and this will be just a plain panel, okay, without circuits. This will be just a panel, PCB panel, and maybe they will have some solar panels, and it will be covered. All right, it will be covered from all the sides. And even this one is the PCB board, which will have solar panels on the bottom side. So let's dive into the simulation. If you want to understand why the values that I'm putting in the simulation, you should refer to the earlier parts of the video where I have described a bit of theory upon what goes on in this random vibration. So this will be just a walk around through the software to setting up things and visualizing the visualizing the results real quick. Okay, let's get started. So first thing to do is to find the simulation tab, right? Simulation tab is right here, and we need to start a new study. If you can't find simulation tab, you just go on SolidWorks add-ins, and there you go. There you can add from there. All right. This random vibration, this is something that I already did, but I'm not going to show you that. I'm going to show you the process. So go to the simulation, create a study, and then select under the linear dynamic there is random vibration. Alright, select that. You can name your simulation random vibration 2. I'm going to write this and click enter. Okay, no, click enter, just click on this OK button. Then it creates a simulation tab right here. Alright, so if you can't find the random vibration, make sure you go here in this tab. Okay, yes, make sure, okay, sorry, okay, wait, it will make you wait. All right, thank you. So there are three options right here. I don't know why it's not loading now. Okay, no problem, just okay. Here are three options and you need to select SolidWorks Simulation Premium. Alright. Okay, randomization 2. I just want to go here because I had already selected that. Alright. Okay, now what we want to do first of all is make sure the connections are understood by the SolidWorks software. To make the connection, we are only focusing here because in this structure, this screw rod is going to hold all the parts. So the connections will be basically on the outer surface of the rods with the inner surface of the holes in all the parts that it is touching. So right click on connections and add local interactions. So you can just use automatically find local interactions and then select the rods. Okay. So in my model, all the four rods are same step files. Alright. So it's selected like that. And then you select these two. Okay. And these three panels for now. So that the software can find the interactions between any of those, right? We are not selecting this outer green panel right now because then it will not just consider the whole connection, but it will also consider the connection with the blocks, but we do not want that. All right. So find local interactions, and then you need to add all the interactions that it actually found. So you can check if the interactions are correct, meaning if they are on the holes and the rod. But even if it is not so, you can just check and remove that connection. Add only the interactions that are correct. For now, it is only creating correct interactions. Okay. Now you need to deselect all the things. So I just select and manually select interactions, and then again select and automatically find local interactions. And then what I need to do is I need to find the interactions between this panel and these rods. Okay, and this panel as well. Because the only way to connect the panel with the rods is by the screw and nut connection in this particular satellite structure. So find local interactions and it finds you exactly 8 interactions for 8 holes that are there on the two panels. Alright. Okay. Now again do this manually and automatically. What we are able to do is, so here if you see, to fix the sliding plate, sorry, the satellite on the sliding plate wheel means again other set of screw rods, right? So for that we need to have a pin connection because we do not have modeled, we have not modeled the rod like this already here. So what we need to do is we need to cross this, cancel this, right? Okay, here it shows all the interactions. We need to right click on the connections and select pin. So what it will do is you can select the surfaces that the pin will attach. Alright, so these two surfaces I want to attach, and then right click and it creates a pin connection. Similarly you can repeat. Okay, you can again go there, pin connections, just select the surfaces where the pin will be. I think you can select multiple as well. Right. Okay. Let me try this. Okay. So you cannot do that. So I just you just have to do one by one. Okay. I just try to be a bit quicker. But no problem. Okay. We have problem again because it's not actually taking. Yeah, I just delete that. You again add the pin because you need to select the surfaces correctly. Okay. Okay. I don't know why it is only showing me pins on the surface. That's above, but you can again come here. You can delete it again. Yes. Okay, just try. I'll try with this. Okay. you got the point, right? You need to give pin fixers. What's happening for this? Don't worry. The worst thing you should do is to panic. All right. So I'll just okay. Here you go. If you don't panic and do it carefully, then it works. Okay. I'll just go. Select the pin. Okay, that's also good. Now I have to do this. I don't know why there is that sky blue ring out there, but I think it's the bug, I think. Okay, and here also, like, what is this? Okay, no problem. I think we have the connections, right? Yeah, I think yeah, it does not look good, right? I will delete it again. Yes. I will try it last one more time. What do I do is I'll select the okay, no, it's not even selecting the surface. Oh, I selected link. Sorry guys. You need to select the pin, okay, not link. Okay, I'm going to leave it like that because I think it is some kind of bug or something like that. But no problem. We have all the connections now, okay? We have the local interactions and the connections. Okay. Okay, after having that, what we want to do is we want to define the material types. Even though in the model you may have defined the material types, it may be the case that the material type is not defined in the simulation. So you need to go there. Here are all the tick marks are there, right? So it means there are indeed material selected, but I'll just show you. Apply or edit material. Okay, FR4 is selected. FR4, this is a custom material, and you can just add you can go to custom plastic and edit the settings, and you can take a screenshot right now and save it later. Pause the video and add these values. Okay, we don't need all the values, we just need to fill those boxes. So the tick marks, so you can see the tick marks here. These tick marks so that the material is already selected. All right, so we have material selected. We have the good connections. Now fixtures. Let's add some fixtures. So we are going to have fixtures along all the edges. All right, because we are assuming that all the edges are going to be uh, fixed in the deployer pod. That might not be the case, but we are going to use this for the simulation. You can add your own fixtures in the way you like. Okay, I've already explained the theory of what we are trying to do here. So all right, the fixtures are also done. Now what I need to do now is we need to add external load. And for the load, what we are trying to do is we are trying to do uniform base excitation. We need to go here and we need to select the acceleration and then the square per hertz and which direction. Like if we want to apply the forces normal to the plane, we select here and let's say a value of 1 right now. All right, so it will apply the forces normal to the plane. Normal to the plane of the rigid body connections. All right, sorry, rigid fixtures. Sorry, yeah. Now we need to set a variation frequency, and we need to edit this, and we need to add some values here. So what values to add here? I've already explained in the theory. I'm just going to show you the actual values. How to add those values here. You just have to first of all, let's check our units. We want it in hertz. So unit hertz. Set user defined name frequency curve, right? what we need to see here exactly. Okay, we need to add some frequencies here, alright? So 20. I'm just going to fill it up. Yeah, this depends on various things that I will explain, that I have already explained in the video actually. If you go to the beginning of the video and then you can check that. Like we'll just add these frequencies. 216. So you just double click on the numbers to like add another entry box of like 3000. I'm going to give it 0 right here. Okay, now after doing this you just click on OK. So you have already edited the curve, edited the PST acceleration. Alright, then you click OK on the base excitation. I think you need to go on again base excitations and edit definitions. Oh, not there, sorry. Details. Okay, go to external, sorry, okay, it's time to add damping. Okay, editor define damping. We just need to do 1/40 here. Okay, it's model damping and it's the damping ratio. We can click on OK. There is another thing that we need to okay, you just go to random vibration and then like details. Oh, sorry, not the details. Sorry. What I'm trying to do is define function curves. Okay, it's not that. Okay, we're not trying to look at the evaluation. What I'm actually trying to do is look at the properties. So in this I just want you to select the automatic solver. Okay, if it's not selected in yours, and in the random vibration options we're doing something. All right, we're going to give it I think I'll just reopen the tab. Something is wrong there. Okay, now it's not giving me the option to select the units right now. I don't know. Let's need to advance options. Okay. Oh, what's wrong, guys? Oh my god, this is like, this will not be happening. Let me save this and try to do this again. Properties and this. Okay, now it's coming. Cycles per hours, right? Okay, so we have given lower limit 20 and 3000 in our data, right? So we need to do this, and we can leave the number of frequency points as it is and just click on OK. Okay, after this I think we need to mesh, right? We need to create a mesh. Create mesh. So creating mesh, let's do a very fine. So as the finer the mesh, the results will be better, but it will also take a long time. Okay, so I think I'll just do some course and I'll show you the I will just compare the results. Okay, so it will create the mesh now. Yeah, as you can see, I have selected a very coarse mesh, so it's not going to be the accurate results. For accurate results, you need to have very fine mesh. Okay, so after that, again go on the simulation tab and I think everything is okay, then you need to run the simulation. Okay, if everything goes right, then the simulation starts running. Wait around, you need to wait around. Okay, it's already solving. Since our mesh is very coarse, it will not take a lot of time, but when I did this one, I had selected a very fine mesh, so it took a lot of time actually. Not that long time, but maybe a couple minutes, I guess. But I think maybe 5 minutes it took. But for this one, it's going to be faster. Okay. Okay. We'll just wait. Yeah, it's now solving. Yeah, it's going to take time, and it depends on your computer, right? And like mine is Dell XPS 15. It has got some GPU, but I'm not sure if it's using it for creating or for solving this. Okay, it's already 82%. Uh, okay, so I think this is the right time for me to advertise my channel. Please subscribe to my channel and like this video if you really if it was really useful for you, if you were rushing to create this simulation, or if you're just trying to know how to do this and later want to learn in deep about it. Yeah, I think that's how sometimes engineers have to do it, right? Because the deadline is always tomorrow for engineers, of course. So yeah, I think it will help you. And come back anytime for this video and look at the first sections to really get to know the theory and stuff. You can open this video on in another tab, and you can follow me, follow the steps as I do with your model, and let me know in the comments how you find this. Okay, yeah. Okay, so we have already got the stress analysis. Okay, I'll give you some information. Okay, so how to make sense of this analysis? All right, so you see the stresses, right? Okay, go over here a little bit bright bright yellow. Okay, you can see here actually. Let me show you. Okay, little bit bright yellow, you see. Okay, in this structure, this is a brass rod, right? And you see this about okay, if you look at this is green color. So about 3.5 to 4.3 times 10 to the power 6 Newton per meter square. So what we want to do is we want to quickly check the yield strength of the brass. Okay. So to check the yield strength of the brass, you can just go to that component, right? Oh man, it's late, right? It's late. I'm enthusiastic about making this video, but it's a bit late. I'm just trying to find the rod. Where was it? Okay, I think we just need to take the brass and find its yield strength. Oh god, this is this is unreal. Maybe like selecting this. Okay, rod step, and then okay, brass. So if you go over here, and if you look at the brass material, you can see the yield strength. So it is 239 Newton per millimeter square. So it's actually if you can convert it in Newton per meter square, and maybe it would come out 2.39 or something like that. Right. So okay, in that case, it might be exceeding the stress, right? So if the part is exceeding the stress, exceeding the yield strength, the stress in the part is exceeding the yield strength, you want to revisit your design and to change the design so that the stress falls under, so that there is no stress greater than yield strength in your part. All right. So another thing we can check is we can go over here and show the displacement analysis. And displacement is quite low for the parts below, like this one, the plates and stuff, because okay, what we are actually simulating is random vibration, uh, and it is suppose the rocket is accelerating on this side. Okay, you can see the arrow of our force, so the acceleration is on this side, and this is being created or deformed. So the deformation is not visually exact, it is just for the visualization. You can check it out, the values here, and the max displacement is just 0.002 mm, I think. Okay, so this was it. I'm going to conclude this video right here. If you have any question, you can put it on the comments below. Thank you for watching.